as we can see, even in ancient times, folks had a hard time reconciling the concept of a God who is with us with a God who is beyond our understanding, who is all powerful, who is all knowing, who is infinite. How do we picture an infinite God being with us? Well, we have to think about what our assumptions are. And I'm going to get into dimension to convince you, like Larry did last time. You know, infinity is more complicated than you think it is. If you didn't see Larry's talk, you need to look it up because he really did a great job with this. So God, who is infinite, is more complicated than we think he is as well. Dimension is similar, right? Dimension is not as simple as we think it is. So we're used to thinking about it in certain ways, and it doesn't always fall out exactly that way. So I'm going to talk you through some of the basics of dimension, and then we're going to get to this connection with the nature of God as we go. All right, so what is dimension anyway? What do I mean by that? Well, there are a couple different definitions people throw around. One is the number of coordinates needed to specify a point in the object. So if the object is a single point and you're at that point, I don't need anything to tell me where you are. I know you're at that point. So this is 0 dimensional. If I have a line segment, though, now it gets more complicated, right? I don't know where you are on the line unless you tell me some information. So if I give it a coordinate system, I tell you, all right, that's going to be part of the real number line. We'll just go from 0 to 1. Now, if you tell me I'm at 0.75, hey, I can figure that out. That's, yeah, maybe about here, right? So I know where you are on the line. If you tell me I'm at 0.259, I'm going to go, well, okay, that's a little over a quarter, so I'm somewhere in there. I know pretty much where you are on the line. You give me any value and I can tell which point it is on the line. What if I get so this is 1 dimensional, right? What if I get what I normally think of as a 2-dimensional object, like a rectangle and its interior? Well, let's do the same thing. So I'm going to put a 0 to 1 axis horizontally and a 0 to 1 axis vertically. And now if you tell me, for example, that you are at 1/2, 1/2, then I'm going to figure you went 1/2 unit over and 1/2 unit up. And so you're right in the middle of this thing. If you're at 1/1, you went 1 unit over and 1 unit up. Oops, lost my thing. 1 unit over, 1 unit. So you'd be right up here in this corner. 2 coordinates tell me where you are in the object. This is 2-dimensional. Similarly, for a 3-dimensional block, I need 3 coordinates to tell where I am there. I'm going to freak you out a little by putting the origin, the place where they're all 0, up here. And the reason for that is that if I put it down here, then this 1 is, well, I can't see it. So you can see it in the picture, right? So if I'm at the point 1/2, 1/4, 0, I would be going 1/2 unit down, 1/4 unit to the right, and then not moving because my third coordinate was 0, so I'd stay here. The third coordinate was 1, I would go back to the back of the block. All right, well, that's one way to think about dimension, and mathematicians like this way, especially algebraists like me, because I can easily think of higher dimensions from here. If I think of dimension as the number of coordinates that I need, then what's the 4th dimension? Well, I'm just going to add a 4th coordinate to my points. And what's the 5th dimension? Well, I'm going to add a 5th coordinate to my points. So I can have infinite dimensional space. I'm just going to keep adding coordinates, as many as I want. Some people like a little more concrete feel to their geometry. So maybe we want to think of dimension instead as the number of mutually perpendicular directions of possible travel within the object. So back to the point. If you're there, well, you are not going anywhere, right? So there's 0 directions of travel. It's 0-dimensional. If you're on the line, well, you can go to the right or you can go to the left. That's 2 directions, but they're not perpendicular to each other, right? They do not form right angles. So there's really only 1 direction of travel. If you're over here in the solid, well, I could choose to go one way and I could go at right angles to that. Now I could have gone at right angles the other way, but that wouldn't be perpendicular to both of these, right? So there's only 2 that are perpendicular to each other. I can't go anywhere else and be perpendicular to both of those things. But if I'm in a solid box, I can go one way. I can go at right angles to that. And then I can go perpendicular to that. Now, that's a little hard to see here. I've got that going back into the box. We often think about it in math and science as a right-hand rule. So I've got 3 axes here. These 2 are perpendicular to each other. These 2 are, if I can move my fingers right, perpendicular to each other. And these 2 are perpendicular to each other. I'm not as flexible as I used to be. Anyway, that's sort of my axis system that can move around with me. Okay, well, this is more insightful, right? Thinking about directions of travel, I can picture that in my mind. Coordinates are a little bit abstract. The problem is, because this isn't as abstract, it's harder for me to move up into higher dimensions. And it's hard for me, I can understand it conceptually that, okay, I now need a fourth direction of travel that's perpendicular to all three of those, but I cannot picture it because I'm sort of trapped in this three-dimensional world in terms of how I can picture things. So that's why I like to go with the coordinate method, because when I have coordinates, then I can go up as high as I want, as many dimensions as I want. Okay, but as I said, things are trickier than that. So with coordinates, we can think of any whole number dimension, but in fact, there are things that are in between dimensions. So let's look at that Koch snowflake a minute. I'm going to start with an equilateral triangle, and we can assume for the moment that all the sides are length 1. Okay, so we're thinking about this side as being length 1, that's length 1, that's length 1. And it's just a triangle, not the part inside, okay, just that boundary. Now here's what I'm going to do. I want you to watch this side as I do it. On each of these sides, I'm going to replace the side with this. I'm going to take out the middle third, and I'm going to put equal lengths to that down like this as a kind of a triangle attached to it. So my path will now go over a third, down a third, back up a third, and then over the final third. So this length 1 thing is now going to become length 4/3, and that's going to be important for what we talk about. So watch that, and over here you'll see what I talked about in terms of taking out the middle third and replacing it, but I want you to see what happens here. Okay, see, so it happened on all three sides, that I took out the middle third and made that part of it longer. Hey, integration of faith and learning, look at that. No, I'm kidding, that doesn't really count, but it is kind of neat when little connections like this come up, like, oh, it's the Star of David in my construction of the Koch snowflake. Okay, now I'm going to keep this process going. So focus in on this side now, and you'll see I'm going to take out the middle third and replace it with a little two-sided triangular path, right? So here we go. I do it on all of them at once, right? So this is the iterative process that I mentioned earlier. Now I'm going to do it again on each of those little tiny sides. I'm going to take out the middle third and bump it out. There we go. And this is about as far as I can draw it so that we can still see anything going on. You can tell it's already starting to look kind of fuzzy. We just keep doing this on into infinity, and we call the end result the Koch snowflake. So it's the boundary of this figure. And as I said, some weird things go on here. Like it's enclosing finite area because it can all be trapped in a circle. But remember, we talked about how each line was replaced. So like when I started with 1, what replaced it was now 4/3. So the thing that originally had perimeter 1 or 3, that triangle, now would have 4/3 plus 4/3 plus 4/3. That's 12/3. So now that has perimeter 4. So the curve is longer. And that happens every time I multiply by 4/3. So it gets longer and longer and longer. And as n goes to infinity, as I iterate this again and again and again, I get an infinite curve. So I have infinite length enclosing a finite boundary, which feels a little weird. Well, what about the dimension of this thing? So normally a curve I would kind of think of as one-dimensional. Even if it's bending, it's not a straight line. You can kind of tell me one point and it would be able to tell me where you are on that line. The Koch snowflake is different. This has what we call fractal dimension, and it's about 1.2619. So now I know what you're wondering. How did you get that number? And please don't tell me if I don't like math, because it might freak me out too much. So I'm going to try not to do that, but I am going to try to tell you where this comes from. First of all, the pieces, I'm not going to go into the computational details, so don't worry about that. The pieces of it are, this is what makes it difficult. First of all, fractions, which if you don't like math and that started in elementary school, fractions is probably what did it to you, so I'm sorry about that. Also logarithms, if you made it through fractions and you stopped liking math in high school, this might be what did you in. So again, sorry about that. And limits, which if you didn't get as far as calculus, you probably never had to do, but they also involve fractions and sometimes logarithms. So we're stuck with that. I'm not going to go into the details of that, but I actually do want to talk to you a little bit about logarithms because they're not as bad as you think. Really, a logarithm is just an exponent. So I think of seeing an expression like log 10 of 100 as asking me a question. What what number would I have to put on 10 as an exponent to get 100? The logarithm is just an exponent. And then I think it's not so hard to see, right? If I square 10, I get 100. 10 times 10 is 100. So 2 is the exponent that I would need. So the log base 10 of 100 is 2. What about the log base 2 of 8? Well, what number do I need to put on 8 as an exponent, on 2 as an exponent to get 8? Well, 2 squared is 4, 2 cubed is 8. So 3 is the number I'd have to put on 2 to get 8. So log base 2 of 8 is 3. I won't torture you with more of those, but I just want to again kind of reiterate that a logarithm is an exponent. It's what you put on the base to get the other number. Now, what is log base 10 of 49? You'll torture you just a little bit more. Well, 10 to the 1 is 10. 10 squared is 100. 49 is somewhere in between there. So the log base 10 of 49 is going to be a number between 1 and 2. So I don't take 10 to the first power. I don't square it. I do something in between. And that's what we're getting at with fractal dimension. But often we get at it by just counting boxes so that we can kind of see are the number of boxes we need to cover this thing one-dimensional, two-dimensional, three-dimensional, or what? What's the exponent? So I'm going to quickly go through this, but I think I can make it understandable. Now, I actually thought I changed this and it did not turn out change. Well, I'll go with this language. So I'm going to call a 1/4 box a segment of length 1/4. Okay, so this is a segment of length 1, and I'm going to think of making a number line with segments of length 1/4. So these are one-dimensional boxes. Okay, and if the number line, if the segment is sitting exactly in there, it intersects 4 of those boxes. And maybe I shift it a little bit. Now it intersects 5 of them, right? 1, 2, 3, 4, 5. But it's not going to intersect more than 5 of them, no matter how much I move it around. So we say that the maximum number of these one-dimensional 1/n boxes is about n. And we're going to keep making n, which is 4 for my example, get bigger and bigger and bigger. So like once it's 1/1,000,000, each of those little things is 1/1,000,000 length. Yeah, whether you're covering 1,000,000 of those or 1,000,000 plus 1 probably doesn't make a really big difference. What if we take that same thing we think of as one-dimensional, we try to put it in a two-dimensional grid? Well, we could put it there so it hits exactly 4 of those boxes. So my side 1/4 squares, I need 4 of them to contain this thing. I could shift it a little, so now it needs 5. I could angle it a little. See if I count there, 1, 2, 3, 4, 5, 6 boxes it needed. So that went up a little bit. But if you think about it, no matter how I put this thing in here, absolute worst case scenario is that it would go down n and over n. Of course, it won't make it that many, right? Because it's still only length 1. So I can't go length 1 down and length 1 over. There won't be enough for the diagonal segment that I put in there. But that's kind of worst case scenario, right? So as n shoots off really high, like once I have 1/1,000,000 by 1/1,000,000 side boxes that I'm covering this with, at most I've got 2n of them. So this is still n to the first power, right? It's that exponent that we're going for. Suppose we put that same segment in a 3D grid. Okay, so I only built one layer of this. So like here, the dark square would be the front of the cube, and the light square back here would be the back of the cube, and then here this side, the edges. Can you kind of picture those? So this is like one layer of cubic subdivided space. Well, again, I'm not going to try to put it there because I don't think we can really see it. But if you put this thing in here, it could go down as far as 4 cubes. These are 1/4 in their sides. It could go over 4. It could go back 4. It's certainly not going to do all of those because it runs out of length. But basically, worst case scenario, you get n plus n plus n of those boxes that you're hitting. So that's 3n. Again, notice the exponent is 1. And when n is super, super huge, the 3 isn't going to make that much difference either. All right, what if we try with something we think of as two-dimensional? So a square and its interior. And I'm going to try to use these same 1/4 boxes, right? These one-dimensional boxes, segments of length 1/4. Well, there's no way I can put enough of them in there to cover the square. It's just not going to happen. So that's because the square is two-dimensional, not one-dimensional, right? It won't fit in a 1 by in a one-dimensional grid. But if we get a two-dimensional grid, now it fits. And it could cover exactly 16 of those little squares, or could cover a little bit more if we move it, shift it around like this one is. Worst case scenario, you're covering like 2 times n squared of the things. So it's kind of way high bad, but notice a square coming in there. If I put it in the cubic grid, now could go down 4, could go over 4, could go back 4. Worst case, you're covering 3n squared. You're not going to pick up a cubic number of these things. So again, that exponent is the important thing. All right, done with that, but let's think about this applied to something like the Koch snowflake. So here's the idea. I start with a big grid and I count how many boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. How many boxes? I've lost track. I think 14 have some of the snowflake in it, right? So this one counts actually because it's got a little, but this doesn't count. That doesn't count, and so on. So I count those up. And then I do it with a smaller grid. So I'm letting my n, the denominator of the side lengths of these boxes, shrink down. Well, n goes up, and then the side goes down. And I have one of these over here, of course, too, and down there. And I count again the boxes that I hit. And then I put in a finer grid. And now I count the boxes that are hit. So we do this finer and finer and finer until we start to converge on an exponent in the number of boxes that we get. And that's where we came up with 1.2619 for the fractal dimension of the Koch snowflake. So let me put this into context of other things that you're more familiar with. If we were doing this idea with the state of Wyoming, this is one of the simplest state boundaries there is, right? 3 sides of it are just totally straight lines. And the fourth one has a little bit of river action going on. Like I think this is the Yellowstone River. And so maybe something a little odd goes on there, but for the most part, that's not going to affect things very much. And so basically, Wyoming has a one-dimensional boundary. Well, what if we look at South Africa? What's the dimension of South Africa's boundary? It's got some smooth parts, but it's got a lot more kind of craggy parts. So there's more interesting stuff going on here. So someone blew up the map and put on these grids on it and got the grid smaller and smaller and smaller and figured out that it's about 1.02 dimensional. So pretty close to one dimensional, but not exactly. What about Britain? Wow, that's a craggy map. There's all kinds of inlets and just stuff all over, promontories, different things that are going to affect the dimension. So again, this was computed as about 1.25 dimensional. So it's not 2-dimensional, the edge, but it's more than 1-dimensional somehow. Okay, what about the surface of a head of broccoli? Now, surface, this is counting each of these little, leaf things as part of the surface. So I'm not talking about the whole clump, but just the boundary part of it, not the insides. And yeah, that's 2.66 dimensional. So that's getting pretty close to 3-dimensional. What about the human brain? So again, just the surface, not the whole thing, but the surface, the outer coating. But the outer coating covers all those little nooks and crannies, right? That are kind of crammed in against each other. So it turns out this is 2.79 dimensional. Now, this is kind of fascinating. So it made me think about neurodegenerative diseases. What do they do to the fractal dimension of your brain? Our brains are pretty efficient. In fact, it's said that we don't use anywhere near all of them. Well, I looked this up. I have not read this article, but just the abstract of the article is really fascinating. And they noted, among other things, that and I can't remember now which one is which. One hemisphere of our brain increases, its fractal dimension increases until adolescence, and then it starts to decrease. The other side increases until adulthood, and then it starts to decrease. The fractal dimension of gray matter in the brain decreases in Alzheimer's patients, but increases in MS patients. The fractal dimension of the white matter in the brain decreases in both ALS and MS patients. So this could at some point be a diagnostic tool for helping doctors understand what they're dealing with in patients. Again, smaller fractal dimension, less efficiency. How about the surface of the human lung? So here's an image. Doesn't, the artist can't draw all the little air sacs and things with as much care as they could, but anyway, because of the limitations of the picture. But think about all those little air sacs in there, and how they are pulling oxygen out of the air and putting it into the blood. Well, that surface, it turns out to be, wow, almost three-dimensional, and that's why they're so efficient at their work. But again, you get a lung disease, and it's going to decrease that fractal dimension. Okay, what about higher dimensions? Well, as I've said, we can add on extra coordinates. That works. Physicists, some physicists anyway, speculate that there might actually be up to 11 dimensions of the world that we live in. Some are wound so tightly up that we can't perceive them. This is actually part of string theory. In fact, the 11th dimension is proposed by superstring theorists. This is not an area of mathematics that I really know anything about, but I'm going to take them at their word for that. We have long talked, not only in science, but in popular culture, about the space-time continuum. Might our sense of time really be our perception of a fourth dimension? In fact, time as a fourth dimension is one of the 11 that physicists talk about. Might God be somehow outside time, so that God's experience of time is not the same of ours? Well, this is not inconsistent with the Bible. Isaiah says that God is eternal. Psalm 90 says that God is from everlasting to everlasting. Even C.S. Lewis got into this and suggested that God is, sorry, I got to see my screen here, all times are eternally present to God. That there's, perhaps it's true that God forever, here's how Lewis put it, sees you in the nursery pulling the wings off a fly. I've not been able to forget that since I read it. He goes on to suggest other things too. Now, I think in my childhood, I never pulled the wings off a fly, but I certainly did other horrible things that I don't like to think about God seeing all the time. I kind of like to think he's focused in on the positive aspects of my life. But this makes me think about forgiveness in a different way, and the importance of forgiveness, and the fact that God's ability to forgive is so different from my own.